An invisible framework holds our entire universe together. We are going to journey to the edge of our understanding to explore the unseen architecture of dark matter, the mysterious substance that binds galactic clusters against the force of cosmic expansion. By the end, you will know exactly how this hidden cosmic skeleton dictates the fate of everything we see in the night sky. We will uncover why galaxies move too fast for their own good, and how scientists map a substance that emits no light. How much of reality do you think remains hidden just beyond our sight? Fritz Zwicky peered into the heart of the Coma cluster and found a puzzle that defied explanation. The galaxies within this vast cosmic gathering were racing around at impossible speeds. According to the established laws of gravity, the collective pull from all the stars and gas we could see was simply not enough to keep them from flying apart. The visible mass was hundreds of times too small to act as a sufficient cosmic glue. Zwicky called this mysterious missing component Dunkel Materie, a name that would echo through the decades: dark matter. His discovery was not just a minor anomaly, it was a fundamental crack in our understanding of the universe, suggesting that the cosmos we see, glittering with stars, is merely the visible tip of a much larger, hidden reality. This forced a profound question upon science. Were the laws of gravity so reliable here in our solar system, breaking down on these immense scales, or was the universe filled with a substance that simply did not interact with light? This single observation set the stage for a revolution, pushing astronomers to consider that the true architecture of the cosmos was built from something we could not see, a hidden framework holding everything together against the relentless pull of dark energy. Einstein's theory gave us a way to see the invisible. His general relativity predicted that massive objects warp the fabric of space and time, bending the path of light itself. This is not just a theoretical idea. We see it happening across the cosmos in a phenomenon called gravitational lensing. Think of it as nature's own magnifying glass. When light from a tremendously distant galaxy travels toward us and passes near a massive galactic cluster, its straight path is curved by the cluster's immense gravity. The result is a cosmic mirage. We might see the background galaxy smeared into a faint arc, or even multiplied into several identical, ghostly images arranged around the cluster's center. The more massive the cluster, the more dramatic the distortion. But here is the profound mystery scientists uncovered. When they measured the total mass of these clusters by adding up all the stars and gas they could see, the numbers did not match the strength of the lensing effect. The gravity warping the light was far, far stronger than the visible matter could possibly produce. It was as if an unseen hand was pressing down on the fabric of spacetime. By carefully studying these distorted images, astronomers can perform a kind of cosmic reconstruction. They can map the precise distribution of mass within the cluster, tracing the outline of the true source of gravity. And every time that map reveals an immense, shapeless halo of dark matter, a hidden scaffold that holds the entire cluster together. This invisible architecture warps the space around it, orchestrating the path of light from the distant universe and giving us our clearest indirect proof that dark matter is not just an idea. It is a physical reality shaping everything we see from our tiny vantage point on Earth. So how did this invisible substance actually build the universe we see today? The story begins in the primordial darkness just after the Big Bang, when the cosmos was a nearly smooth, expanding sea of energy and particles, but it was not perfectly smooth. Tiny, random fluctuations in density were imprinted upon the fabric of space, and dark matter, responding only to gravity, was the first to feel their pull. These minute ripples were the gravitational seeds around which everything would eventually grow. Think of dark matter as the sturdy, invisible framework of a building, while ordinary matter, the gas and dust that would become stars and planets, was like loose construction material scattered by a strong wind. Without that stable framework to cling to, the ordinary matter would have simply been blown away by the relentless force of cosmic expansion, drifting forever in the void. It was dark matter's additional, powerful gravitational pull that created deep enough wells for gas and dust to fall into, cool down, and finally coalesce into the first proto-galaxies. This process was made possible by a critical property of dark matter. It is what scientists call cold, meaning its particles moved relatively slowly in the early universe. This slow, deliberate motion allowed it to clump together efficiently, forming knots and filaments in a vast cosmic web. We can watch this cosmic history unfold inside supercomputer simulations. When models are run with only ordinary matter, the result is a sparse, disappointing universe with gas too spread out to form any significant structures. But when the cold, clumping nature of dark matter is added to the simulation, the outcome is breathtaking. An intricate, web-like structure emerges from the digital void, with galaxies forming exactly where the dark matter filaments intersect, mirroring our own observed universe with stunning accuracy. This is why dark matter is far more than a placeholder for missing mass. It is the essential architectural blueprint, the hidden mold that gave shape to the cosmos and set the stage for the birth of stars, planets, and ultimately us. These digital universes allow us to witness the impossible, watching as a smooth, featureless expanse transforms over billions of years into a complex cosmic tapestry. Supercomputers perform this magic by calculating the gravitational dance of countless dark matter particles. They begin with the tiny density ripples imprinted after the Big Bang, then let gravity do its work, pulling those particles together over cosmic time. The result is not a random scattering, but the emergence of a precise architecture, a vast web of dark matter filaments connecting at dense nodes, separated by enormous, empty voids. This predicted structure is not just a theoretical fantasy. It matches with stunning accuracy the actual large-scale structure of our universe that astronomers painstakingly map. Projects like the Sloan Digital Sky Survey have charted the positions of millions of real galaxies, and they reveal the same immense web-like pattern. The simulations and the sky surveys tell the same story. They confirm that dark matter forms the fundamental skeleton of the cosmos, but these virtual universes do more than just confirm. They act as cosmic laboratories. Scientists can tweak the properties of the dark matter in the simulation, testing whether it is cold, warm, or something else entirely, and see which version grows into a universe that looks like our own. So far, the cold dark matter model produces a cosmic web that is a near-perfect match for reality, predicting where galaxies should form and how they should cluster together. This virtual reconstruction reveals that every galaxy we see, from our own Milky Way to the most distant island of stars, is nestled within a much larger, invisible halo of dark matter. The size and shape of that hidden halo dictated where and when a galaxy could be born, guiding the placement of everything we see across the vastness of space. These invisible halos are not just vague clouds of mystery. They possess a specific, measurable structure that scientists can map through their gravitational influence. Observations combined with powerful simulations reveal that a dark matter halo forms a roughly spherical shape around a galaxy, with its density increasing dramatically as you move toward the center. This predictable density pattern is so consistent that it can be described by a mathematical model, a kind of universal blueprint for how dark matter arranges itself. The most famous of these is known as the Navarro-Frenk white profile, a formula that captures how the halo's density spikes sharply at the core before gently tapering off into the vast emptiness between galaxies. This hidden sphere of influence extends far, far beyond the luminous edge of a galaxy's stars. The visible galaxy we see in telescopes is just a small, bright kernel embedded within an immense, invisible sphere of dark matter that contains most of the galaxy's total mass. This is why the halo so completely dominates the galaxy's gravitational field. Its presence dictates the very motion of stars within the galactic disk. When astronomers first measured how fast stars orbit around the center of spiral galaxies, they expected the outer stars to move more slowly, just as Pluto orbits the Sun much slower than Mercury. But that is not what they found. The orbital speeds of stars remained flat, not dropping off with distance. The only explanation for these constant high speeds is the gravitational pull from a massive, unseen envelope of matter, a dark matter halo whose gravity reaches out to grip even the farthest stars. This gravitational footprint even shapes the distribution of smaller satellite galaxies around a larger host, arranging them in a broad, spherical swarm that mirrors the outline of the invisible halo itself. Ultimately, the precise structure of these halos, the exact shape of their density profiles, offers our best clue to the true identity of dark matter. Different theoretical candidates, from slow-moving cold particles to faster-moving warm ones, would each leave a unique signature in the halo's core density and overall shape. By mapping this invisible architecture in finer and finer detail, we are not just studying a ghost, we are reading the fingerprint of a substance that built the cosmos. The Bullet Cluster gave us a cosmic collision that revealed the invisible in stunning detail. Two immense galaxy clusters, each containing hundreds of galaxies, slammed into one another in an event of almost unimaginable violence. In such a collision, the different components of the clusters behave in profoundly different ways. The galaxies themselves, vast as they are mostly empty space, so they pass by each other like swarms of ghostly ships in the night. But the majority of the ordinary, visible matter in a cluster is not in the stars. It is in the form of a superheated, thin gas that fills the space between the galaxies. When the clusters collided, this tenuous but pervasive gas could not avoid a direct hit. The clouds of gas from each cluster rammed into one another with tremendous force, creating a shockwave and slowing down dramatically. This violent interaction caused the gas to heat to extreme temperatures, making it glow intensely in X-ray light, which our space telescopes could clearly see. So, in one part of the sky, we had a precise map of where the ordinary matter was concentrated, a brilliant splash of hot gas caught in the middle of the cosmic pile-up. Then astronomers turned to a different tool, gravitational lensing, to map the true distribution of mass. By measuring how the cluster warped the light from galaxies behind it, they could trace the invisible gravitational landscape. The result was a revelation. The map of total mass, the true source of gravity, was not centered on the glowing X-ray gas. It had sailed right through the collision, largely unaffected, and was now located in two separate, distinct clumps far away from the gas. The majority of the stuff that makes up the clusters had simply passed through the entire event as if it weren't even there. This was the moment dark matter's ghostly nature was laid bare. It does not interact with itself or with ordinary matter in any significant way, except through the force of gravity. It feels no pressure, creates no friction, and emits no light. This single observation delivered a critical blow to alternative ideas that tried to explain away dark matter by modifying the laws of gravity. Those theories struggled to explain how gravity could be strongest in a region of space that was largely empty of the visible matter that supposedly sourced it. The bullet cluster stands as a pivotal piece of evidence, a cosmic snapshot that separates the seen from the unseen and shows us that the true architects of our universe are entities we are only just beginning to sense. But what if the answer is not an invisible substance, but a flaw in our understanding of gravity itself? This is the radical proposition at the heart of modified Newtonian dynamics, or MOND. In the 1980s, physicist Mordechai Milgrom suggested that on the vast, sparse scales of galaxies, where gravitational pulls become incredibly feeble, Newton's famous laws might simply work differently. In this framework, there is no mysterious dark matter. Instead, the unexpectedly high speeds of orbiting stars are explained by a subtle change in the rules. At extremely low accelerations, the force of gravity could become slightly stronger than our standard formulas predict. It is a compelling idea, a cosmic loophole that rewrites the rules of motion to fit the observations without needing to fill the universe with an undetectable particle. For individual galaxies, MOND works remarkably well, often predicting the observed rotation curves with impressive accuracy. It feels like an elegant solution, a way to fix the math without inventing a whole new form of matter. Yet this elegant fix begins to fray when faced with the full complexity of the cosmos. The bullet cluster presents an almost insurmountable challenge. How can a modification of gravity explain why the primary source of gravity in that system is completely divorced from the location of the visible matter? A tweak to the law of gravity should still tie gravity directly to the stuff we see, not separate it into two distinct entities that pass through one another. Furthermore, the detailed structure of the early universe, imprinted in the cosmic microwave background, shows a specific pattern of ripples that cold dark matter models replicate with stunning precision. Reproducing that same pattern with modified gravity requires introducing additional, complex elements that begin to look very much like a different kind of dark matter. This ongoing scientific debate is not a failure. It is the engine of discovery, the tension between these two ideas, an unseen particle versus a rewritten law, pushes physicists to design ever more clever and precise tests. Each new observation, from the delicate motions of distant stars to the subtle distortions of spacetime, acts as a referee in this grand contest of ideas. We are witnessing a fundamental struggle to describe reality, where the outcome will reshape our most basic understanding of the cosmos. So if dark matter is real, what is it actually made of? The hunt for its true identity has led physicists to propose some truly exotic candidates. Among the most compelling are particles known as WIMP, or weakly interacting massive particles. The name itself tells their story. They would be massive, perhaps dozens or even hundreds of times heavier than a proton, yet they interact with ordinary matter only through the weak nuclear force and gravity. This makes them incredibly difficult to detect, passing through our planet and even our bodies as if we were not even there. They are a natural prediction of theories beyond our current standard model of physics, such as supersymmetry, which posits that every known particle has a heavier, unseen superpartner. If WIMP are the answer, they might occasionally annihilate each other when they collide, producing a faint drizzle of gamma rays that our most sensitive space telescopes could, in theory, pick up. A different kind of candidate takes a completely opposite approach. The Axion is a hypothetical particle that is unimaginably light, potentially trillions of times less massive than an electron. It was originally proposed to solve a deep puzzle in the physics of the strong nuclear force. individually, an axion would be a ghost of a particle, but collectively, a vast, cold sea of them could permeate every corner of space, their combined gravitational pull shaping the cosmos. This idea that the universe's missing mass could be made of something so light and numerous is a powerful reminder of how strange the solution might be. The search for these phantoms is underway in extraordinary places. To shield experiments from the constant background noise of cosmic rays, scientists have built ultra-sensitive detectors deep inside mountains and in abandoned mines, waiting for the impossibly rare moment a dark matter particle might nudge an atomic nucleus. Other experiments use powerful magnetic fields to try and convert passing axions into faint microwave photons. We are also looking to the skies, scanning for the indirect signals of dark matter annihilating or decaying in the hearts of galaxies or within the diffuse halos that surround them. Catching just one of these particles would be a discovery of monumental importance. It would not just solve the dark matter puzzle, it would rip open a door to an entirely new realm of physics, revealing forces and particles we have never dreamed of. The true nature of this hidden architecture is the final piece in our cosmic map, waiting to be found. Deep beneath the Black Hills of South Dakota, in a former gold mine turned into a modern cathedral of science, one of humanity's most sensitive experiments waits in darkness. This is the LUX Zeppelin detector, a vessel filled with 10 tons of liquid xenon so pure it must be shielded from the faintest whisper of background radiation. Its entire purpose is to sense the unimaginably rare event, the single, gentle nudge of a dark matter particle striking the nucleus of a xenon atom. To achieve this, the experiment had to solve a profound problem. The surface of our planet is constantly bombarded by cosmic rays, a hail of high-energy particles that would completely drown out the subtle signal of a dark matter interaction. The solution was to go deep underground, where a mile of solid rock acts as a natural shield, filtering out nearly all of that interference. Inside its titanium cryostat, the xenon is chilled to -100 degrees Celsius, a state of ultra-quiet readiness. If a WIMP, one of those hypothetical dark matter particles, were to pass through, it might, just might, collide with a xenon nucleus and produce a tiny flash of light and a wisp of electric charge. Arrays of exquisitely sensitive light sensors, known as photomultiplier tubes, line the top and bottom of the tank, watching relentlessly for that single, telltale photon. Similar efforts are underway around the world, like the Xenon NT experiment housed deep under a mountain in Italy. These are not simple machines. They represent the absolute pinnacle of our engineering, designed to isolate a signal so faint it tests the very limits of what is possible to measure. Yet, after years of data collection across multiple generations of these detectors, the screens remain quiet. No confirmed signal has ever risen definitively above the ever-shrinking background noise. This profound silence is itself a form of discovery. Each null result places a stricter limit on how strongly dark matter can possibly interact with the ordinary matter we are made of. It tells us that if dark matter is a WIMP, it is an incredibly shy one, interacting with far less force than we once hoped. This ongoing absence challenges the very core of our assumptions. Are we looking for the right thing in the right way, or is dark matter even more alien, more detached from our reality than our best theories predicted? The search is forcing a moment of deep introspection in physics, pushing us to consider that the ultimate architect of the cosmos might not just be hidden, but engineered from something entirely beyond our current imagination. While our underground detectors listen in profound silence, other telescopes are tuned to a different kind of signal, one born from cosmic violence. If dark matter particles are their own antimatter counterparts, then a collision between them would not be a gentle nudge. It would be an act of mutual annihilation, transforming their combined mass directly into a flash of pure energy. This energy would materialize as a shower of other particles, most notably a cascade of high-energy gamma rays. This is the promise of indirect detection. We may not see the dark matter itself, but we could observe the fiery aftermath of its destruction. To hunt for this faint signature, scientists point powerful instruments like the Fermi Gamma Ray Space Telescope toward places where dark matter should be at its most densely packed. The serene, star-poor dwarf galaxies that orbit our Milky Way are perfect hunting grounds. These tiny galaxies are thought to be dominated by immense halos of dark matter, with very few conventional astrophysical processes that could create gamma rays. If researchers see a persistent, unexplained excess of gamma rays emanating from such a quiet region, it could be the long-sought signal. The very center of our own galaxy is another prime candidate, a place where the gravitational well is so deep that dark matter should be concentrated into a seething, invisible core. The challenge is immense. The galaxy is a chaotic marketplace of natural gamma ray producers, from spinning pulsars to the remnants of supernova explosions. Picking out a specific excess attributable to dark matter annihilation is like trying to hear a single, unique instrument in a roaring symphony. Yet, by meticulously modeling and subtracting all the known cosmic contributions, any stubborn, residual signal that remains becomes profoundly interesting. At the South Pole, a different kind of observatory is listening for another byproduct of this annihilation. The ice cube detector uses a cubic kilometer of pristine Antarctic ice as its sensor. When rare, high-energy neutrinos from space pass through, they can interact with the ice and produce a faint flash of blue light. If a spike of these neutrinos were ever traced back to a region of high dark matter density, it would be another powerful, indirect clue. A confirmed signal from any of these methods would do more than just prove dark matter exists. It would crack open its identity. The specific energy of the detected gamma rays would reveal the mass of the annihilating particles. The intensity of the signal would tell us how often they interact with one another. This indirect approach turns the entire cosmos into a vast particle collider, one that operates on a scale we could never hope to build on Earth. We are using the universe itself to experiment on its most fundamental components, searching for the ghostly fingerprint of annihilation written in the language of light. The faint, cold glow of the cosmic microwave background is the oldest light in the universe, a fossilized echo from a time when everything was fundamentally different. This afterglow of the Big Bang fills every cubic centimeter of space, a relic from when the cosmos was just 380,000 years old. Back then, the universe was a hot, dense plasma, a searing fog of particles and light. As it expanded and cooled, atoms finally formed, allowing light to travel freely for the first time. That first flash of liberated light is what we detect today, stretched by 14 billion years of cosmic expansion into a uniform microwave signal. But this signal is not perfectly smooth. Super-precise measurements from missions like Planck have mapped its minute temperature variations, revealing a speckled pattern of slightly hotter and colder spots. These tiny fluctuations are cosmic hieroglyphics, a coded message detailing the exact composition and fate of our universe. Decoding this pattern has given us our most accurate cosmic recipe. It tells us that dark energy makes up about 68% of the universe. Ordinary matter, the stuff of stars and planets, is a mere 5%, and dark matter constitutes a staggering 27% of everything. This cosmic inventory is not a rough estimate. It is a precise measurement etched into the very first light, confirming that the universe we see is utterly dominated by unseen components. The specific pattern of these hot and cold spots is a direct imprint of sound waves rippling through the primordial plasma. The physics of these waves depends critically on the gravitational influence of dark matter. Its gravity provided the necessary pull to amplify those initial density ripples, acting as the gravitational anchor that allowed structures to begin forming. The size and distribution of the spots we observe are a perfect match for a model where dark matter is cold, moving sluggishly in the early universe. This slow, deliberate motion was essential. It allowed dark matter to clump together efficiently from the very beginning, creating the gravitational wells that would later trap ordinary matter and build the first galaxies. If dark matter had been warm, moving at a significant fraction of light speed, its rapid motion would have smoothed out these small-scale ripples, preventing the formation of the smallest galaxies we observe today. The cosmic microwave background is therefore more than a snapshot. It is the universe's original architectural blueprint, a foundational pillar of modern cosmology that confirms not only the existence of dark matter but its fundamental properties. This ancient light whispers that the cosmos was built from the bottom up, with the slow, steady gravity of cold dark matter laying down the invisible scaffolding for everything to come. That ancient echo of the Big Bang is not the only fossil we can use to measure the cosmos. Another, more subtle imprint was left behind in the very arrangement of the galaxies we see today. In the universe's first few 100,000 years, it was a seething ocean of plasma where light and matter were locked in a constant struggle. The intense pressure from photons of light created waves, much like sound waves, that rippled outward through this hot, dense fluid. These were the Baryonic acoustic oscillations, and they traveled at a staggering speed until the moment atoms formed and the universe became transparent. At that instant, the waves froze in place, leaving a permanent, faint signature in the distribution of matter. This signature gives us a standard ruler etched across the sky. The distance those waves traveled before freezing is known with incredible precision, providing a fixed measuring stick billions of light years long. When astronomers look at the universe today, they can still see this ruler's imprint. Galaxies have a subtle, but statistically significant, tendency to be separated by this specific hallmark distance. It is as if the cosmos is stamped with a faint, recurring pattern, a cosmic fingerprint left over from its earliest moments. Massive projects like the Sloan Digital Sky Survey have mapped the three-dimensional positions of millions of galaxies, and by analyzing their distribution, they can clearly detect this BAO signal. By seeing how this standard ruler appears to our instruments, whether it looks stretched or squeezed, scientists can measure how the fabric of space itself has expanded over cosmic time. This provides an independent and powerful way to trace the history of the universe's growth. The measurements from this galactic mapping consistently confirm the same cosmic recipe first revealed by the cosmic microwave background. They find that the amount of dark matter needed to explain the growth of these vast structures is exactly what the ancient light predicted. This is a powerful cross-check, like two completely different witnesses telling the same story. The gravitational pull of dark matter was the essential force that guided where galaxies would eventually form. It sculpted the large-scale structure of the universe, determining the placement of the immense filaments and voids that make up the cosmic web. By using baryonic acoustic oscillations, we are not just measuring expansion. We are reading the architectural plans written by dark matter itself, confirming that this unseen framework has been dictating the layout of the cosmos since the very beginning. This deepening cosmic mystery now confronts us with a fundamental disagreement over the very speed of our universe's expansion. Our most precise measurements of the Hubble constant, the number that describes how fast the cosmos is stretching, are telling two different stories depending on when we look. Observations of the early universe, anchored by the cosmic microwave background, give us one value. Yet when we measure the expansion using stellar mile markers like supernova in the more recent universe, we get a consistently faster, different result. This is the Hubble tension, a stubborn discrepancy that refuses to go away. It suggests a crack in our standard model of cosmology, a hint that something is missing from our cosmic equation book. One compelling possibility is that dark matter itself is the source of this discord. Perhaps in the universe's first moments, dark matter was not completely inert. What if it interacted with radiation or with itself in some subtle, early way we have not yet accounted for? Such an interaction could have altered the size of the primordial sound waves imprinted on the cosmic microwave background, the very standard ruler we used to calculate the early expansion rate. If that ruler's length was different than we assume, then our entire inference of the Hubble constant from the ancient light would shift, potentially bringing it into alignment with the modern measurements. This idea transforms dark matter from a passive scaffold into an active player with a hidden history. Its properties might have evolved over time, its influence on the cosmos changing as the universe cooled and expanded. The Hubble tension is more than a technical disagreement between datasets. It is a profound invitation to rethink the nature of the cosmos's dominant ingredient. It pushes us to consider models where dark matter is not simply cold and collisionless, but possesses a richer, more complex physics that left its mark on the expansion history of everything. Solving this puzzle requires peering into the dark sector not as a single, static entity, but as a dynamic force whose story is woven into the fate of the universe itself. Yet these cosmic giants are not the only place we find clues. The smallest and most ancient galaxies in the universe, the faint dwarf galaxies that orbit larger hosts like our Milky Way, offer a uniquely pure view into dark matter's heart. These tiny, dim collections of stars are so dominated by their invisible halos that they are essentially cosmic laboratories, stripped of the complex astrophysical noise that complicates studies of their larger cousins. Their simple structure and lack of swirling gas and dust make them ideal for testing our most fundamental ideas about how dark matter should behave. But when we look closely, these quiet laboratories are revealing profound puzzles. According to the most straightforward simulations of cold dark matter, the density of a dark matter halo should spike dramatically toward its center, forming a sharp cusp. Yet observations of many dwarf galaxies suggest something different, a much shallower profile with a constant density core. This is the core cusp problem, a persistent mismatch between prediction and reality that has troubled astronomers for decades. How could the dark matter in these galaxies appear to be less concentrated than our best models insist it should be? One compelling idea points to the violent lives of stars. Even in these small galaxies, periods of intense star formation can lead to supernova explosions. The collective force of these stellar blasts could literally push and churn the central dark matter, effectively smoothing out the dense cusp into a shallower core over billions of years. Another puzzle arises when we compare the number of large, dense dark matter subhalos our simulations predict should orbit a galaxy like the Milky Way to the number of actual dwarf galaxies we can see. The simulations produce an overabundance of massive, ready-made dark matter clumps that are seemingly too big to fail at forming stars. Yet we do not see nearly as many bright dwarf galaxies as these hefty halos should host. Where are all the missing galaxies? This too-big-to-fail problem suggests that either star formation in these small halos is far less efficient than we thought, or there is something about the dark matter itself, perhaps an ability to interact with itself or with other particles that prevents these small-scale structures from forming or surviving as predicted. These small-scale discrepancies are not merely minor details. They are critical stress tests for the entire cold dark matter paradigm, probing the fundamental physics of dark matter in a way that the large-scale cosmic web cannot. The serene, simple dwarfs are forcing us to ask if dark matter is even more complex and dynamic than the simple, cold particle we have long imagined. Vera Rubin peered into the heart of the Andromeda Galaxy and found a motion that defied the cosmos itself. She was measuring the speeds at which stars orbit their galactic center, expecting a very specific pattern. According to Kepler's laws of motion, so reliable within our own solar system, stars farther from the center should move much more slowly, just as the outer planets in our system crawl along their orbits compared to the inner worlds. But the data told a different story entirely. The stars, from those near the bright core to those on the faint, distant edges, all raced along at nearly the same incredible speed. This was the flat rotation curve, a graph that should have been a steeply falling line but was instead a stubborn, unwavering flat one. The visible galaxy alone could not possibly hold these outer stars in such a tight, fast grip. Their velocity was a silent scream, testifying to the presence of a hidden source of gravity. This invisible mass had to be arranged in a vast, spherical halo, extending far beyond the last visible star, its gravitational pull reaching out to keep every orbiting star in check. Rubin's work did more than add evidence for dark matter. It fundamentally redefined what a galaxy is. We can no longer see them as simple islands of stars. They are instead complex gravitational systems where the glittering disk of light is merely a small, bright decoration embedded within an immense, unseen sphere of influence. The stars we see trace out the shape of the galaxy, but the dark matter defines its true weight and power, an invisible hand that dictates the very motion of the cosmos. These galactic metropolises, the largest structures held together by gravity, are a testament to an invisible ruler. Within a single cluster, thousands of individual galaxies race through the void at speeds of millions of miles per hour. If the only gravity at work came from the stars and gas we can see, this entire cosmic city would have flown apart eons ago. The sheer velocity of these galaxies should have shattered the cluster, sending its members spiraling off into the emptiness between. That they do not is the most dramatic proof of a hidden hand at work. We can weigh this invisible anchor using several methods at once, creating a powerful convergence of evidence. By measuring the velocities of the galaxies themselves, astronomers can calculate the total gravitational pull needed to keep them on their orbits. This is like watching cars race around a vast, invisible track and deducing the shape and mass of the track itself from their speed alone. These measurements point to an immense source of gravity, one that far exceeds what is visible. Then we look at the superheated gas that fills the space between the galaxies. Observations from X-ray telescopes show this gas is searingly hot, glowing with intense energy. It can only remain trapped in such a dense, hot state if it is confined by the gravitational pull of a truly massive object, a deep well of gravity carved out by dark matter. Finally, the subtle distortions of gravitational lensing map the cluster's total mass directly, tracing the outline of the primary source of gravity. When all these lines of evidence are combined, they tell a consistent story. In these colossal clusters, the glittering galaxies and the glowing hot gas, all the ordinary matter we can possibly detect, accounts for a mere 10 to 20% of the total mass. The rest, a staggering 80 to 90%, is the unseen architecture of dark matter. This hidden framework does more than just provide weight. The specific paths that galaxies take as they orbit within the cluster's gravitational well are like historical records. Their orbits reveal the precise shape of the dark matter density profile, telling us how this invisible mass is distributed from the crowded core to the sparse outer edges. This distribution is a frozen echo of the cluster's violent formation, a history of mergers and growth written in the language of gravity. By studying the dynamics of these vast systems, we are using the universe's largest scales as a cosmic balance, placing dark matter on a weighing pan of unimaginable size to confirm that it is the true governor of the cosmos's most massive structures. The James Webb Space Telescope now turns its golden eye toward the cosmic dawn, seeking the moment our universe first flickered to life. Its extraordinary infrared vision allows it to cut through the dust of time, collecting the faint, stretched light from the very first galaxies to emerge from the darkness. These nascent islands of stars are the perfect test subjects for our ideas about dark matter. According to our models, the first structures should have formed inside the gravitational wells of the earliest dark matter halos. Gas drawn in by the halo's pull would have cooled and collapsed into the first brilliant stars. Webb is now checking that blueprint against reality. By analyzing the shapes and rotation of these primordial galaxies, astronomers can trace the invisible hand that guided their birth. If a young galaxy rotates too fast or holds a shape that visible matter alone cannot explain, it is a direct signal of its hidden dark matter skeleton at work. This is like finding the fossilized imprint of a long-vanished mold. The properties of these first galaxies, their brightness, their sizes, and how quickly they assembled, are all dictated by the nature of the dark matter that anchored them. Webb's deep field observations are also creating maps of unprecedented detail. By observing how the collective gravity of distant clusters and filaments warps the light from even more remote galaxies behind them, the telescope is refining our weak lensing maps to a precision never before possible. This allows us to trace the distribution of dark matter across the vast cosmic web as it existed billions of years ago, watching how the invisible scaffolding evolved over cosmic time. Each new image from Webb is more than a pretty picture. It is a data point in a grand cosmic experiment, one that tests whether our understanding of dark matter holds true at the very beginning of everything. By illuminating the universe's dark ages, this observatory may finally show us how the ghostly architecture of the cosmos first decided where the lights would turn on. A new eye in the sky is now charting the invisible architecture of the cosmos with unprecedented precision. The Euclid Space Telescope, designed not to look at individual stars but to survey billions of galaxies across a third of the sky, is our most ambitious attempt to create a three-dimensional map of the dark universe. Its primary mission is to solve the riddle of dark energy, the force accelerating cosmic expansion. But to do that, it must first perform an exquisite dissection of gravity's two faces. It must separate the lingering, structural pull of dark matter from the repulsive push of dark energy. It does this by observing two subtle cosmic fingerprints. The first is cosmic shear, the minute warping of distant galaxy images as their light passes through the vast, webbed filaments of dark matter that fill the space between us and them. This effect is incredibly faint, a distortion smaller than 1% of a galaxy's apparent shape, but by measuring it for billions of galaxies, Euclid can trace the detailed distribution of the dark matter scaffolding itself. The second fingerprint is the clustering of galaxies, the specific patterns in how galaxies group together, the distances between clusters and the sizes of the voids, are a direct record of how the cosmic web has been stretched and pulled over time by the competing influences of dark matter's gravity and dark energy's push. By comparing this grand three-dimensional map of the present-day universe with the ancient blueprint imprinted on the cosmic microwave background, Euclid can watch a cosmic movie of structure formation. It can see if dark matter has behaved exactly as the cold dark matter model predicts, clumping together precisely to build the web we see, or if its influence has waned or changed on the largest scales. Any deviation would be a monumental discovery, pointing toward a richer, more complex dark sector than we have imagined. The mission's data will place the most stringent constraints ever on how strongly dark matter particles might interact with each other or with radiation, and it will measure the precise equation of state of dark energy, determining if its repulsive strength has remained constant or changed over the life of the universe. Euclid represents a fundamental shift. We are no longer just searching for dark matter or just measuring dark energy in isolation. We are studying them as the twin engines of cosmic destiny, a hidden matter that builds and a hidden energy that tears apart. The fate of everything from the largest galactic cluster to the smallest dwarf galaxy hangs in the balance of their silent, invisible war. This ghostly architecture might not be as silent as we once believed. What if the particles of dark matter can occasionally collide with one another, communicating through a subtle, unseen force? This is the compelling idea behind self-interacting dark matter, a model where these invisible particles do not just pass through each other like perfect phantoms. They can scatter, transferring energy and momentum in rare, gentle encounters. The implications for the cosmos would be profound. In the dense core of a dwarf galaxy, for instance, these self-interactions could act as a form of invisible friction. As particles collide, energy is siphoned from the inner, fastest-moving regions and transferred outward. Over billions of years, this process could gradually smooth out the predicted sharp density cusp, transforming it into the shallower, constant density core that astronomers observe. It is a cosmic balancing act where the microphysics of an invisible particle dictates the macroscopic shape of a galactic halo. The drama of colliding clusters, like the bullet cluster, also takes on a new dimension under this model. While the dark matter would still largely pass through the collision, a small but significant fraction of particles could interact, creating a subtle drag. This could explain why in some mergers the dark matter appears slightly offset from the galaxies it leads, a detail that the simplest cold dark matter model struggles with. These self-collisions would leave a unique signature in the aftermath of such cosmic crashes. Current astrophysical data allows for this possibility, pointing toward a very small but real chance for dark matter particles to interact. The search is now on to find the specific fingerprint of these interactions in the detailed shapes of galaxy halos and the precise dynamics of merging systems. Exploring self-interacting dark matter beautifully illustrates a deep connection in cosmology. The tiniest properties of a fundamental particle, a cross-section measured on a subatomic scale, can ripple upward to shape the grandest structures in the universe, governing the evolution of galaxies themselves. This idea ties the fate of the largest cosmic cities directly to the hidden conversations of their smallest, invisible constituents. Perhaps the dark matter weaving through the cosmos is not a sea of tiny particles at all, but a population of ancient, shadowy objects born from the universe's first chaotic moments. These would be primordial black holes, hypothetical remnants from a time of extreme density, just instants after the Big Bang. In this scenario, pockets of the hot, expanding universe could have collapsed directly under their own intense gravity, forging black holes of almost any size. They could range from the mass of a small asteroid to that of many stars, all forming long before the first star ever flickered to life. These primordial black holes would be the ultimate ghosts. They would interact with the rest of the universe only through their gravity, clumping together in vast, invisible halos around galaxies. perfectly mimicking the gravitational effects we attribute to particle dark matter. So how could we ever hope to find such an object? One method is through a phenomenon called microlensing. If a primordial black hole were to pass directly between Earth and a distant star, its gravity would act as a tiny lens, bending the starlight and causing the star to temporarily brighten in a very specific way. Astronomers have scanned millions of stars for these telltale flashes. The results have been profoundly informative, yet inconclusive. These extensive searches have largely ruled out the possibility that all dark matter is made of primordial black holes across a wide range of masses, particularly those similar to stars. If such objects were as common as dark matter requires, we would have seen countless more of these microlensing events than we actually have. Yet the door is not completely closed. A widespread population of asteroid mass black holes, each no larger than a small moon, could still be hiding in the darkness. Their tiny individual lensing signatures are incredibly difficult to detect with current technology. Alternatively, larger, intermediate mass black holes could also form a component of the dark matter, provided they are rare enough to have evaded our microlensing surveys. The mergers of these ancient black holes would also be a source of the gravitational waves we now routinely detect with observatories like LIGO and Virgo. The existence of black hole mergers whose components are too heavy to have come from dying stars would be a compelling, though indirect, piece of evidence for this primordial population. This idea forces a fundamental rethink of dark matter's identity. Is it a vast collection of the smallest things imaginable, or is it a legion of the most gravitationally powerful objects in existence, both born from the fury of the Big Bang? The answer will determine whether we must look for new physics in the quantum realm or in the fossil record of the cosmos's very first second. This invisible substance holds the ultimate fate of the cosmos in its hands. The long-term destiny of our universe, whether it will expand forever into a cold, dark emptiness or eventually collapse back upon itself, hinges on a delicate tug of war between two unseen forces. On one side is dark matter with its relentless gravitational pull, constantly working to slow down the cosmic expansion initiated by the Big Bang. On the other is dark energy, the mysterious repulsive force that is doing the exact opposite, pushing galaxies apart at an ever-increasing rate. Our current best model of the universe, known as lambda CDM, paints a specific picture of this cosmic endgame. In this future, the expansion driven by dark energy will ultimately win, but the structural integrity provided by dark matter will not be entirely broken. Galaxies will continue to drift apart from one another into an ever-deepening isolation, but the individual structures themselves, the galaxies and clusters held fast by their dark matter halos, will remain gravitationally bound islands in an immense, growing void. The stars within them will live out their lives, but no new stars will form as the last reservoirs of gas are depleted or flung into the intergalactic darkness. It is a future of preservation within a sea of separation, yet this forecast rests on the assumption that dark matter is stable and unchanging. What if it is not? Speculative theories suggest that dark matter could possess more complex properties. What if, over trillions of years, dark matter particles could slowly decay into lighter, even more elusive particles? Such a gradual loss of the universe's primary gravitational anchor would fundamentally alter the balance of power. With the restraining hand of dark matter's gravity slowly weakening, the acceleration driven by dark energy would proceed unchecked at an even faster pace. This could shift the cosmic trajectory from a slow, inexorable drift to a more dramatic and destructive finale. Alternatively, other models propose a different kind of end, a big rip, where dark energy grows in strength so dramatically that it overcomes every force in nature, from galactic clusters down to the very atoms that make up our bodies. While this scenario is primarily tied to the nature of dark energy, the amount and behavior of dark matter set the initial gravitational baseline against which this terrifying repulsive force must compete. The properties we are trying to measure today, the slowness of its particles or its potential for self-interaction, are not just academic curiosities. They are variables in the universe's ultimate equation, parameters that write the final chapter for everything that exists. Contemplating this role transforms our view of dark matter. It is not merely the hidden architect of the past, the scaffold upon which galaxies were built. It is also the silent arbiter of the future, the unseen hand that will guide the cosmos to its final state, long after the last star has flickered out. Our entire understanding of reality has been built upon what we can see and touch, a perspective that now appears profoundly limited. The revelation that most of the universe is composed of a substance fundamentally alien to our own existence delivers a powerful blow to our cosmic self-importance. For centuries, humanity placed itself at the center of creation, but dark matter teaches a different lesson. We are not the standard stuff of the cosmos. We are the rare exception, the 5% anomaly swimming in a sea of invisible, unknown matter. This forces a deep philosophical question. If 85% of the physical universe is made of something that does not interact with light, something that passes through our bodies and our planet without a trace, how complete is our comprehension of existence? Our senses and our most powerful tools are tuned to perceive only a tiny sliver of what is actually there. It suggests that reality, in its full form, is far stranger and more vast than our human-centered viewpoint ever allowed us to dream. This is not a scientific problem alone. It is a fundamental challenge to our place in the grand scheme, a humbling reminder that the universe is under no obligation to be immediately intelligible to us. This profound mystery, however, has sparked a global endeavor that transcends borders and rivalries. The search for dark matter has become one of the most collaborative projects in human history. Scientists from nations around the world are pooling resources and intellect, building detectors deep underground and launching telescopes into the void of space. This shared quest for understanding, fueled by our innate curiosity, is driving technological revolutions. The need to see the unseen has pushed us to create ever more sensitive sensors and powerful computers, innovations that ripple out to benefit society in countless ways. This journey into the dark is a testament to our species' resilience and imagination. It reflects a choice to face our ignorance not with fear, but with a determined humility, pushing the boundaries of knowledge forward one careful experiment at a time, forever redefining what it means to explore. A profound elegance lies at the heart of modern particle physics, a theoretical symmetry so beautiful it demands the existence of an entirely new cosmic landscape. This is supersymmetry, an idea proposing that every single particle we know, from the humble electron to the lofty Higgs boson, has a hidden, heavier twin. For every matter particle, there is a force-carrying superpartner, and for every force particle, a matter-based twin. This doubling of the cosmic cast is not just for aesthetic appeal. It solves one of the most nagging theoretical problems in physics, known as the hierarchy problem, which questions why the force of gravity is so unimaginably weaker than the other fundamental forces. More importantly for our story, supersymmetry provides a perfect home for dark matter. The lightest of these superpartners would be stable, unable to decay into anything else, and would interact with ordinary matter only through gravity and the weak nuclear force. It would, in essence, be a WIMP, a weakly interacting massive particle, emerging naturally from the mathematics as the ideal candidate for the universe's missing mass. In the hot, dense conditions of the early universe, these particles would have been created in abundance, colliding and annihilating in a fiery thermal dance. As the cosmos expanded and cooled, they would have frozen out, leaving behind precisely the relic abundance we now measure as dark matter. It is a breathtakingly elegant solution, tying together the very large and the very small into one coherent picture. Yet nature has so far been reluctant to reveal this symmetry. The Large Hadron Collider, our most powerful microscope, has searched tirelessly for any sign of these superpartners. Its colossal detectors have watched countless proton collisions, recreating conditions not seen since the first moments of the Big Bang. So far, the data shows only the particles of our known standard model. This profound silence has placed stringent constraints on the simplest versions of supersymmetry, pushing the predicted masses of these hidden particles into territories that are harder and harder to reach. The absence of a discovery is itself a form of guidance, forcing theorists to refine their models and consider more complex, hidden sectors. This intimate interplay between the cosmic and the subatomic is a defining feature of the quest. The failure to find supersymmetry at the collider does not kill the idea, but it deepens the mystery, suggesting that the dark world may be even more secluded and complex than we hoped. The search for dark matter's identity and the hunt for supersymmetry are two fronts in the same war, a campaign to read the hidden blueprints of reality. A discovery in one would instantly illuminate the other, cracking open the door to a far richer and more complete understanding of the universe than we have ever known. Our cultural imagination has painted dark matter in shades of fantasy and power. In stories like Philip Pullman's His Dark Materials, it appears as a shimmering, conscious dust that bridges parallel worlds, a source of mystical energy and profound connection. Video games and films often cast it as an unstable power source for futuristic weapons or a volatile substance capable of tearing reality apart. These narratives are compelling because they personify the unknown, turning a cosmic mystery into a tangible force for heroes and villains to wield. Yet the scientific reality is far stranger and more subtle. The very property that makes dark matter so elusive, its refusal to interact with the electromagnetic force, makes the fictional depictions impossible. You cannot bottle a particle that passes through solid lead as if it were empty space. You cannot weaponize a substance whose components drift through your own body by the trillions every single second without a single trace of their passage. This constant, ghostly rain is utterly harmless, a testament to its profound detachment from the world of light and matter we inhabit. The gap between these thrilling fictions and the quiet facts highlights a crucial challenge in science communication. When media sensationalizes complex ideas for dramatic effect, it can seed lasting public misconceptions, making the already difficult task of understanding the cosmos even harder. But these creative interpretations also serve a deeper purpose. They are not failures of understanding, but a testament to human curiosity. They show how a scientific mystery can capture our collective imagination, becoming a modern symbol for all that remains just beyond our grasp. Dark matter in fiction becomes a stand-in for the great unknown, a blank canvas upon which we project our hopes for cosmic connection and our fears of uncontrollable power. By exploring where these stories diverge from science, we do more than just correct facts. We open a window into how humanity grapples with the truly incomprehensible, using myth and metaphor to find our place in a universe dominated by the unseen. This relentless search for an invisible cosmic component has quietly built a legacy of innovation right here on Earth. The extreme technological challenges of detecting something that barely interacts have forced us to become better engineers, pushing the boundaries of the possible. To hear the faint whisper of a dark matter particle, scientists needed to create the quietest listening posts in history. This demand gave rise to astonishing advancements in ultra-low background materials. Imagine creating metals so pure that their own intrinsic radioactivity does not drown out the signal you are trying to find. This is not just clean, it is a level of purity once thought unreachable, achieved by selecting and refining materials with a painstaking precision that now benefits other fields. The need to operate at temperatures near absolute zero has driven cryogenics to new heights, developing systems that can maintain a stable, ultra-cold environment for years on end. These are not laboratory curiosities. The same data analysis techniques developed to sift through billions of events in search of one genuine dark matter signal are now being adapted to improve medical imaging, helping doctors spot the faintest traces of a tumor in a scan. The sensitive light sensors perfected for these detectors are finding uses in security screening, able to identify materials with unprecedented accuracy. Even the field of quantum computing benefits from this pursuit, as the quest to control quantum states at the single particle level aligns perfectly with the sensitivity required to sense the cosmos's most elusive substance. This technological cascade is a direct result of aiming for a target we cannot yet see. These international collaborations have become engines of global partnership. Projects like LIGO, which detected gravitational waves, and the upcoming Darwin detector, a next-generation liquid xenon observatory, are not owned by a single nation. They are shared endeavors, uniting scientists from dozens of countries who pool their intellect, resources, and cultural perspectives to tackle a problem far greater than any one of them. This shared infrastructure fosters a continuous exchange of knowledge, building diplomatic and scientific bridges that last for generations. Funding this kind of basic, curiosity-driven research is often viewed as a gamble, yet history consistently shows it is one of the most reliable investments society can make. The World Wide Web was invented at CERN to help physicists share data, a side effect of their pursuit of fundamental particles. The same is true for dark matter exploration. We set out to map the hidden architecture of the universe, and along the way, we inadvertently seed the ground for technologies that reshape our world in tangible, often unexpected ways. This journey into the dark does not just answer cosmic questions, it builds a brighter future, proving that the value of reaching for the stars is often found in the new tools we create to make the attempt. This vast cosmic puzzle is not just for professional scientists in ivory towers. Anyone with a curious mind and an internet connection can now join the hunt, contributing to discoveries that shape our understanding of the invisible universe. Online platforms like Galaxies have turned the search for dark matter's fingerprints into a global, collaborative effort. The challenge is immense. Modern sky surveys produce millions of images of galaxies, far too many for any small team of researchers to analyze on their own. This is where the power of the human eye and brain becomes an invaluable scientific tool. Volunteers from all walks of life log on and are presented with real, raw telescope images, then asked simple but profound questions. Does this galaxy have a spiral shape? Do you see any strange arcs or multiple images around it that could be a gravitational lens? Each classification made by a volunteer is a small piece of a massive data analysis project, helping to map the dark matter web by identifying the very lenses that trace its outline. The collective power of this human network is extraordinary. Citizen scientists have been responsible for spotting rare and peculiar galactic systems that automated computer algorithms might have missed entirely. Their keen observations have led to the discovery of new, faint dwarf galaxies, those pristine dark matter laboratories, and identified bizarre galaxy mergers that serve as crucial tests for our models. This direct public participation accelerates research at a pace that would otherwise be impossible, creating a living, breathing partnership between the scientific community and the global public. This process does more than just crunch data. It builds a bridge transforming abstract cosmic concepts into a tangible, shared journey of exploration. By participating, people gain a first-hand appreciation for the careful, often repetitive work that underpins major breakthroughs, demystifying the scientific process. It fosters a profound sense of connection, a reminder that the quest to understand our place in the cosmos is a fundamentally human endeavor, one that we can all be a part of, one galaxy at a time. This cosmic framework we inhabit might be just one room in an infinite mansion of realities. The multiverse hypothesis, a speculative but profound idea, suggests our universe with its specific dark matter profile is merely one possibility among countless others. In this vast cosmic landscape, each separate universe could be a pocket with its own unique set of physical laws and fundamental constants. Some of these universes might contain no dark matter at all, while others could be dominated by forms of it that interact so strongly they form dark stars and dark planets, entire invisible cosmic ecosystems. The strength of gravity, the mass of particles, the very rules of existence could be rewritten in these other realms. This leads to a staggering thought. The precise amount of dark matter in our universe, 27% of everything, appears finely tuned for a specific outcome. If there were much less, its gravitational pull would have been too weak to gather gas into the first galaxies. The cosmos would be a dark, sterile sea of drifting hydrogen. If there were much more, its gravity would have crushed those early structures into supermassive black holes long before stars could ever ignite. In both of these alternative scenarios, life as we understand it would be an impossibility. This apparent cosmic fine-tuning has led some physicists to consider the anthropic principle. The idea is not that the universe was designed for us, but rather that we can only find ourselves in a universe capable of producing us. We exist, therefore we must live in one of the rare pockets where the dark matter abundance, purely by chance, fell within the narrow window that allows for galaxies, stars, planets, and ultimately, observers. This shifts the question from why our universe has dark matter to why we find ourselves in this particular universe that has it. While this remains a highly speculative frontier of thought, it fundamentally reframes the nature of our search. It challenges us to ask whether dark matter is a necessary component of any conceivable cosmos, or if it is simply a contingent feature of our own local reality, one thread in a tapestry of infinite variation. This mind-bending concept expands the discourse from pure astrophysics into the realm of metaphysics, forcing us to question not just what dark matter is, but what it means for the very nature of existence. The gravitational pull of a dark matter halo does more than just herd stars and gas. It orchestrates a deeper, more subtle cosmic choreography, one that might even shape the invisible magnetic fields woven through the spaces between galaxies. These vast, tenuous magnetic fields are a profound mystery in their own right, and their origins have long puzzled astronomers. How do such immense structures, spanning hundreds of thousands of light years, become so strong and so organized? The answer may lie in the hidden hand of dark matter. While dark matter itself is thought to be utterly neutral, unmoved by magnetic forces, its gravity sets the entire stage for magnetic drama. By sculpting the deep gravitational wells that galaxies and clusters sit within, dark matter dictates the flow of ionized gas. This superheated, electrically charged plasma is the raw material for magnetism, and as it swirls and churns within the dark matter's grip, it acts like a gigantic dynamo. These motions can stretch and twist weak, primordial magnetic fields, amplifying them into the powerful cosmic forces we detect today. The specific shape and density of the dark matter halo, therefore, controls the efficiency of this natural generator. A more massive, concentrated halo creates a deeper gravitational well, leading to faster, more turbulent gas motions that can potentially forge a stronger magnetic field. This provides a compelling link between the unseen architecture of dark matter and another great cosmic puzzle. It suggests that the magnetic map of a galaxy is not just a product of its visible stars and gas, but a direct imprint of its hidden gravitational skeleton. By studying the strength and configuration of these magnetic fields, we might be able to trace the outline of the dark matter halo itself, reading its structure through an entirely new lens. This connection reveals the true pervasiveness of dark matter's influence. Its ghostly presence is not confined to governing orbits alone. It whispers through the fundamental forces of the cosmos, shaping realities we once believed were entirely separate, proving that the universe's hidden framework touches everything, even the forces we cannot see. The dense heart of our own Milky Way should be a dark matter furnace. According to our best models, the gravitational pull of the supermassive black hole and the surrounding stars has dragged immense quantities of dark matter into the galactic core, creating a region where the particles are packed together with extraordinary density. In such crowded conditions, if dark matter particles are their own antimatter counterparts, they should be constantly colliding and annihilating, transforming their mass into a cascade of energy and new particles, including a predictable drizzle of high-energy gamma rays. This is the promise that drives observatories like HESS in Namibia and MAGIC in the Canary Islands. These are not traditional telescopes with lenses and mirrors. They are arrays of giant curved mirrors that stare up at the night sky, waiting for the fleeting flashes of Cherenkov radiation, a faint blue glow produced when gamma rays from space strike our atmosphere. They are tuned to see the universe in photons of tremendously high energy, the very signature we would expect from heavy dark matter particles meeting their end. And they have seen something. From the direction of the galactic center, there is a detectable excess of these very high-energy gamma rays, a signal that, at first glance, looks tantalizingly like it could be the long-sought proof. The challenge and the reason for continued debate lies in the sheer chaos of the galactic downtown. This region is a vibrant astrophysical metropolis, buzzing with natural particle accelerators. Rapidly spinning pulsars send out lighthouse-like beams of radiation. The remnants of ancient supernovas blast particles to near light speed, and other exotic objects create a cacophony of high-energy emission. Distinguishing a potential dark matter signal from this roaring background is like trying to isolate a single, unique instrument in a symphony orchestra playing at full volume. The ambiguous data means that the same observed gamma rays can be explained by a population of yet undiscovered pulsars or by the annihilation of a specific type of dark matter particle. This forces scientists to build increasingly sophisticated models that account for every possible astrophysical source, a painstaking process of elimination. The search in these crowded regions presents a formidable challenge, demanding a perfect marriage of particle physics theory and astrophysical observation. It is a reminder that the universe rarely makes its secrets easy to find, forcing us to listen ever more carefully for that faint, ghostly voice whispering from the core of our own galaxy. Our own cosmic backyard holds a puzzle written in the arrangement of its smallest galaxies. Around the Milky Way, astronomers have mapped the orbits of dozens of dwarf satellite galaxies, and they do not swarm in a random, spherical cloud as many simulations of cold dark matter predict. Instead, they appear to dance in a startlingly thin, rotating plane, a vast disk-like structure that circles our galactic core. This is the plane of satellites problem, a cosmic anomaly that seems to defy our simplest expectations for how these dark matter-dominated clumps should behave. If the standard model is correct and galaxies form within sprawling, roughly spherical halos of dark matter, then their satellite companions should arrive from all directions over cosmic time, settling into a messy, unorganized swarm. The existence of such a delicate, coherent disk feels, to some, like finding all the scattered marbles in a room have neatly arranged themselves into a single, spinning circle on the floor. How could such a structure form and persist? The answer may lie in the complex interplay between the invisible and the visible. Perhaps the dark matter halo of our galaxy is not a simple, featureless sphere, but possesses its own subtle infrastructure, a lopsided or flattened shape that naturally guides satellites into a preferred plane. Or maybe the ordinary matter holds the key. As these small galaxies plow through the Milky Way's extended gaseous halo, they could experience a form of cosmic drag, their orbits gradually synchronizing and settling into a shared disk over billions of years. This would mean that the visible universe is not just a passive passenger on the dark matter scaffold, but an active participant that can, in turn, reshape the distribution of its own building blocks. This puzzle has also reignited interest in alternative dark matter scenarios. If dark matter were warm, composed of lighter, faster-moving particles, it would suppress the formation of the very smallest subhalos. This would leave fewer satellite galaxies overall, and those that did form might be more likely to be born within a gas-rich disk early in the galaxy's history, naturally falling into a planar arrangement from the start. Similarly, if dark matter particles can interact with one another, that subtle friction could erase the smallest clumps and smooth the halos of larger ones, potentially making it easier for a disk of satellites to emerge and survive. The delicate dance of these faint galaxies is far more than a curiosity. It represents a critical stress test, a fine-scale probe of dark matter's fundamental properties. The grand cosmic web matches our models perfectly, but it is here, in the local motions of our smallest neighbors, that we might find the first tiny cracks in the theory, hints that the invisible architect of our cosmos operates by rules more nuanced than we ever dreamed. This invisible cosmic architecture might even hold the key to life itself. The vast halos of dark matter that cradle galaxies do more than dictate the motion of stars. They create the underlying environmental conditions that could make a planet habitable or hostile. Within the spiral arms of a galaxy like our own, the density of dark matter is not uniform. It forms a complex landscape of hills and valleys of gravitational influence. In regions where this dark matter is densely packed, its gravitational pull can stir up the galactic disk, potentially leading to faster rotation rates and more frequent close encounters with other stars. Such stellar flybys could disrupt the delicate orbits of comets in a system's outer reaches, sending a hail of icy bodies inward in a potential extinction-level event for any emerging biosphere. The ghostly presence of dark matter might therefore influence the very clockwork of cosmic catastrophes. Beyond gravity, there is another, more subtle threat. If dark matter particles can annihilate upon contact, these dense regions would become natural power plants of high-energy radiation. A planet orbiting a star in such a neighborhood would be bathed in a constant, elevated background of gamma rays and cosmic particles. This persistent radiation could strip away atmospheres over geological timescales or directly damage complex organic molecules, creating a profound challenge for the origin and evolution of life. It acts as an invisible filter, potentially sterilizing entire swaths of a galaxy before life ever gains a foothold. Conversely, the galactic suburbs where the dark matter halo thins out may offer a far more tranquil setting. Here, stellar orbits are more stable, catastrophic encounters are rarer, and the radiation environment is calmer. This quieter cosmic neighborhood could provide the extended periods of planetary stability necessary for life to experiment, evolve, and grow in complexity without constant cosmic interruption. When we search for habitable worlds, we have traditionally focused on the Goldilocks zone around a star, where temperatures are just right for liquid water. But this new understanding introduces a galactic habitable zone, a region within a galaxy where the dark matter density is neither too high nor too low, creating a safe harbor for biological evolution. The invisible hand that built the galaxies may also be quietly drawing the maps for where consciousness can ultimately arise. This connection ties the fate of a potential civilization to the deepest, darkest foundations of the cosmos, suggesting that the universe's unseen framework is not just a physical structure, but a fundamental player in the story of life. Neutrinos add a ghostly whisper to the cosmic conversation, a stream of nearly massless particles that pour through the universe at almost the speed of light. They were once a promising candidate for dark matter itself, earning the label of hot dark matter for their blistering velocity, but we now know they are far too light and swift to build the universe's framework. Their incredible speed meant they could not settle down into the small, dense clumps that act as the seeds for galaxies, instead streaming freely out of these nascent structures and smoothing them over. This free streaming effect left a subtle but distinct signature on the cosmic blueprint, subtly suppressing the formation of the smallest galaxies and altering the statistical distribution of matter across the cosmos, what cosmologists call the matter-power spectrum. While their individual mass is almost nothing, their staggering abundance means that together, neutrinos contribute a tiny but measurable fraction to the universe's total mass budget, a faint gravitational presence alongside the dominant dark matter. Future experiments like the Deep Underground Neutrino Experiment, or DUNE, aim to measure the precise properties of these phantoms, determining their exact masses and how they oscillate between different types. This deeper understanding will sharpen our cosmological models, allowing us to disentangle the subtle gravitational effects of neutrinos from the overarching influence of dark matter. This intricate relationship shows us that the cosmos is not built by a single, monolithic force. It is a delicate interplay, a cosmic symphony where the high-speed flight of neutrinos provides a soft, high-pitched counterpoint to the deep, structural base of cold dark matter. Together, they weave the complex tapestry of structure we observe, a reminder that even the most fleeting of phantoms can leave a permanent mark on the architecture of everything. Our scientific journey is built upon learning to see without light. Isaac Newton watched an apple fall and deduced an invisible force pulling it to the earth, a tether of gravity that reached across empty space to hold the moon in its orbit. He described its effects with mathematical precision, yet he openly admitted he could not fathom its true nature, famously stating, "I frame no hypotheses." A century later, Michael Faraday visualized the space around a magnet as filled with lines of force, an intangible field that could push and pull. His contemporaries struggled with this idea of an invisible reality, yet these fields became the bedrock of our modern world, enabling everything from electric motors to wireless communication. We could not see radio waves, but we learned to harness them. We could not photograph a black hole, but we inferred its presence from the furious dance of stars around an empty point. Each of these conceptual leaps was met with resistance, a natural hesitation to accept a reality that defied common sense. Dark matter is simply the latest chapter in this grand tradition of discovery. It is not an anomaly but a continuation of a pattern where our tools and our reason reveal layers of existence hidden from our primal senses. This historical perspective offers a powerful lesson in humility and patience. The mysteries that confound us today, the ghostly particles that slip through our detectors, are likely the foundations of tomorrow's understanding. They remind us that the universe is under no obligation to conform to the limits of our current imagination. Just as Faraday's fields once seemed like mystical speculation, the true nature of dark matter may one day become as fundamental to our technology and our world view as the invisible waves that now carry our voices across the planet. The story of science is the slow, persistent lighting of a dark room, revealing wonders where we once saw only emptiness. The next generation of dark matter hunters is already taking shape in deep underground laboratories and in the silent void of space. These new observatories are not just upgrades, they represent a fundamental leap in our ability to listen for the faintest of cosmic whispers. The LZ experiment, the successor to LUX Zeppelin, will be even larger and more exquisitely quiet. Super CDMS will use advanced cryogenic sensors to feel for the slightest vibration from a passing particle, and ADMS will continue its patient search for actions, tuning its massive magnetic fields like a cosmic radio dial, hoping to catch the faint hum of these ultra-light phantoms converting into microwave photons. Together, these missions are designed to probe the last remaining hiding places for the most popular dark matter candidates, the WIMP and Axions. If they are there, we are building the traps that will finally catch them. Above the Earth, a different kind of observatory is preparing for launch. The space-based gravitational wave detector, LISA, will open an entirely new window on the cosmos. While its primary goal is to observe the mergers of supermassive black holes, it has a hidden potential. It could detect the ripples in spacetime produced by the merging of primordial black holes. If a significant population of these ancient objects exists, their collisions would send gravitational waves ringing across the universe, offering compelling, indirect evidence that dark matter is not a particle at all, but a legion of cosmic fossils from the first instant of time. This multi-pronged assault on the mystery is our best strategy yet. But what if, after all this, the detectors still come up empty? What if the WIMP and Axions are not there to be found? This profound silence would force a radical shift in our thinking. Physicists would then turn to even more exotic scenarios, contemplating the existence of an entire dark sector. This would be a hidden realm of reality with its own family of particles, governed by its own forces, interacting with our world only through the slender, fragile thread of gravity. In this vision, dark matter would not be a single, simple particle, but a complex and vibrant hidden universe living parallel to our own. The coming decades promise to be a golden age for this search, driven by a powerful synergy. Breakthroughs in particle detector technology will be fed by new astrophysical data from next-generation telescopes, with all of it crunched by increasingly intelligent computer simulations. This collaborative effort, uniting fields that once worked in relative isolation, is our greatest strength. The ultimate outcome, whether it is a definitive detection or a deeper, more puzzling absence, is guaranteed to reshape our fundamental understanding of reality. The quest to identify the unseen architect of the cosmos is far more than a technical challenge. It is a journey that will ultimately redefine our place within the vast, hidden structure of everything. Our journey through this invisible architecture reveals a cosmos built from shadows, a framework that dictates the form of everything we see. We have traced its ghostly outline through the warped light of distant galaxies, felt its gravitational grip in the impossible speeds of orbiting stars, and watched its blueprint emerge in the grand simulations of a digital universe. From the primordial seeds of the Big Bang to the vast clusters that define the cosmic web, the evidence converges on a single, humbling truth. A substance we cannot see, touch, or illuminate governs the universe through gravity alone, its silent presence the ultimate architect of reality. This is not a failure of our instruments, but a testament to the profound limits of our perception, a reminder that most of the cosmos operates in a realm forever beyond our direct experience. As we stand at the brink of a new era, with next-generation telescopes and underground laboratories pushing the boundaries of the detectable, we are not merely hunting for a particle. We are seeking to complete our map of existence, to finally put a name to the force that sculpted the heavens. The greatest mysteries are not walls that block our path, but horizons that invite us onward, demanding our curiosity and rewarding our perseverance. This invisible scaffold does more than hold galactic clusters together against the relentless pull of expansion. It connects us, here on our tiny, vibrant world, to the vast and mysterious engine of the universe, a silent partner in the cosmic story that allowed our galaxy, our sun, and our planet to form. What does this hidden cosmos make you wonder about? Share your thoughts on these cosmic wonders in the comments below.